All right, we're going to continue on with Unit 4. This is 4.3. I can understand function fundamentals. Function fundamentals. So we're going to talk about some more important aspects of functions. So the warm-up here is from 8th grade or from previous classes. I'm hoping you know that when you hear the word rate, you should automatically be thinking of the word slope. A lot of times we use rate and slope interchangeably, especially when we're talking about a graph. So let's go ahead and take a look at this paragraph right here. Most of the time, there's really nothing special about the letters that we're going to use to represent functions. We can use any letter we want. A lot of times we use F. That's by far the most common, but we also use the letters G and the letters H, although we're not just limited to those. We could use any one we want. So no matter what letter we use, the independent variable, it's usually X, but again, we might use a T or a Q or whatever it happens to be if it makes sense in that particular situation. That X is the independent variable. That's what we plug into the function, and the dependent variable would be f of X, or the function value at that particular X value. Okay, so remember that f of X is the same as y. Remember, if we write it this way, we can see what we plugged in and what we got out, so we can kind of see the XY pair. So the ordered pairs that we graph don't always have to be thought of as xy pairs. They can be thought of as x, f of X pairs. And so that what that means is instead of labeling things always as an x and y axis, we can also label the axes, the x-axis and the f of X axis, or the x-axis and the g of X axis, and so forth. So one of the big ideas that we're going to be talking about this year, and make sure we're clear on this is a big idea. It's that functions make shapes when we graph them. Functions make shapes when we graph them. And we call the most basic shape a function makes, we call it its parent graph, or we call that the parent function. That's like the original shape. We might change it in some fashion, but the original shape, that kind of standard shape that we're after, we call that the parent function. Now, if a shape is common enough, then we give it a special name, and we're going to deal with 3 basic types of functions in this class. So we're going to call this first one f of X. And when f of X makes this type of shape down here, then we call it a piecewise function. A piecewise function. And if you think about it, the name kind of makes sense because it's basically just a bunch of pieces of lines stuck together. So we've got a line right here, and a line right there, and a line right there. This is not the only type of piecewise function, but this is the type of piecewise function that we're going to deal with in this particular class. So we're going to call this next one g of X. If g of X makes this type of shape right here, I'm hoping everybody knows what this is called. Because it makes a line, it's called a linear function. And again, the name of that makes sense. So now let's look at the last one. So I've got f of X here, I've got g of X here, and then this one we're going to call h of X, not for any particular reason, but we're just going to call it h of X. And when a function makes this particular type of shape, this is called an exponential function. So exponential function. Now we're going to talk about why we call that an exponential function a little bit later on. But one thing I want to point out, just so you can kind of get this in your head and start it cooking, this exponential function kind of runs along here along the x-axis, just above the x-axis, crosses right here at 1, and then gets bigger and bigger and bigger and bigger. Okay, so it gets closer and closer to the x-axis as we go out toward this left end, but it never actually touches it. And there's a name for that type of behavior. That's actually called an asymptote. Okay, so I'll say that again. That's called an asymptote. So an asymptote is a line that approximates the graph. So what happens is it gets out here really close to that line. It just gets closer and closer, but never actually touches it. So it really gets flat and kind of looks like a line out on that end, whereas on this end it just gets really, really steep. All right, so as we've seen from previous practice problems, it's really important to know the vocabulary that we use with functions, and we've got to be able to find function values from the graph or from the equation. So we want to find the domain and the range and the function value for these things that are up above. So we're going to use this one for f, this one for g, and then this one over here is going to be h. So we want to talk about the domain here. So again, we're going to use that squish technique. We're going to squish everything down here and this up here. So we would have a domain, the x's, the independent variable, going from -4 all the way to 5. So from -4 to 5. And remember, those endpoints are included, so we're actually going to make sure that these are included in our interval notation, so like that. And then the range, we'd squish everything onto the y-axis. So if you think about it, I'm going to start down here, and then we don't actually get any answers until we get right here. Like this one would come over here and hit that. These would come over here. And then we have a whole bunch of points that would kind of double up on this part right here. And then we don't have any answers up there. So what I'm going to do is I'm going to start down here. We start getting answers right there. It goes all the way up to here, and then it stops right there. So writing this down in interval notation, we'd start in the y direction from -1, and then we'd go all the way up to 3. And we'd do closed brackets on each one of these because those endpoints are included. It actually touches 3, and it actually touches -1 right there. Now we want to figure out what f of 1 is, and remember how we do this. This is the x value. This is the independent variable value. So we plug in a 1 and we want to know what we get out. So what that means is go to 1 on the x-axis and then either go up or down to make sure that you're on the graph. So we're going to go over 1 and we have to go up to 3. So the function value here is 3. And again, you can see what the point is over 1 and up 3. There's the x value. There's the f of x value, or the function value for that particular x. So let's take a look at this one. We've actually seen these before. So we could slide these points up here, these points down here, squish it onto the x-axis. The domain for this is from -infinity to infinity. All real numbers would work there. And then in the y direction, we start getting answers way down here, and they go all the way up there. So again, the range is going to be from -infinity to infinity. And then we want to find g of 1. So we're going to go to 1 on the x-axis, and we're going to go up or down to get on that point. So this is 1, 1. So we plug in a 1, we get out a 1. Again, you can see that xy value there. All right, domain on this one right here. So notice that we've got this arrow that goes way out there. It's right along, it's kind of shading right along the x-axis there with that asymptote. And then this goes up and up and up and up and up and out. So we could take these points and slide them down here. They cover everything, and the further up we go, the further out we go. So it would actually cover everything over there. So the domain on this one is also going to be -infinity to infinity. But then we get something kind of interesting, and this is why I mentioned this behavior on this asymptote before. If we were to take these points and squish them over onto the y-axis, they would definitely cover from here to here, and then these other ones would cover from there to there. So I hope everybody would agree we don't get any y values, no function values down here, but we start getting values right around 0 or so. So right around right there. So we're going to start at 0, and then we continue going. You can go as high up as you want. There's really no limitation there, so we're going to go to infinity. But my question is this: if it never actually touches the x-axis, it never actually has a function value of 0. It never actually hits that right there. So we'd actually have a round bracket around that. And then we want to find h of 1. So we're going to go over to 1 on the x-axis, and it just so happens on every one of these we have to go up, but if we had to go down, we'd do that. But that point right there is 1, 2. So we plug in a 1, and we get out a 2. All right? So there's the domain and range for each one of those. There's the function values found from each one of those graphs. Again, we've got piecewise, we've got linear, and we've got exponential. Now, I do want to recall a couple of other fundamental terms and some vocabulary that we need to be aware of. So again, we can use some words like increasing, decreasing, and constant to describe those functions. When we look at the graph, as we go from left to right, and that's important, increasing functions go up as we go from left to right. Decreasing functions go down from left to right. And constant functions just stay the same. They're perfectly flat. And I also want you to keep in mind, we know what a y-intercept is. A y-intercept is where the graph crosses the y-axis. So that means an x-intercept is where it crosses the x-axis. And most graphs have an x and a y-intercept. And intercepts are a really big deal. It's really important that you know what intercepts are, how to find them, and how important they are for a graph. And it's actually possible to have more than one x-intercept, but not more than one y-intercept. So I want to slide up here, and I want to take a look at these as far as intercepts go. So you'll notice that this touches the x-axis right here, touches the y-axis right there. So this would be an x-intercept, that would be a y-intercept, and this would be another x-intercept. So on this one, we've got two x-intercepts. We only have one y-intercept. It only crosses the y-axis in one place, only crosses the y-axis in one place, and only crosses the y-axis in one place. You might think about, well, why can we only have one y-intercept? Well, watch what would happen if I had another y-intercept right here. Like, let me do this in blue Say it came down like that or something weird. Okay, what that means is it wouldn't be a function anymore. Okay, since the y-axis is a vertical line, we can only cross that vertical line once. So what I'd like to do is slide down here, and you can look up above. I've got actually copies of those same functions, or the graphs of those same functions at the top of the next page. But you look up above and it says this. Describe each of the functions as increasing, decreasing, or constant, or a combination on their domains, and state the x and y intercepts and write them as ordered pairs. So let's take a look at this one right here. If we're talking about increasing, decreasing, or constant, well, it's kind of going up from here to here. So it's increasing on this little interval right here. Then it's flat. It's constant there, right there, and then it's decreasing over here. So we're going to put that this is a combination. So this is a combination, okay? And then on this one right here, this one's clearly going up from left to right, so this would be increasing. That would be an increasing function. And then this one, it's really flat over here, but it does go up just slightly, just barely going up, and then it really takes off here. So this is also an increasing function. Okay, and now we're going to talk about the intercepts. So the intercepts are where it crosses the x and the y-axis. So I'm going to write down xint. Those are going to be the x-intercepts. So on this one right here, it crosses the x-axis at -4, and it also crosses at +4. But remember, we want to write these as ordered pairs. So it crosses at -4, 0, and crosses at 4, 0. So this one happens to have 2 x-intercepts. And then the y-intercept would be right here. The y-intercept would be 0, 3. So let's turn our attention to this one right here. This one happens to cross the x-axis at 0. So the x-intercept would be 0, 0. And the y-intercept is the same thing. It only crosses at one point. If a function does that, if it crosses at the origin, that's going to be an x and a y-intercept. And then let's take a look at this one. Again, some interesting behavior here. As far as the x-intercept goes, does it ever actually cross the x-axis? Does it ever touch the x-axis? We said above that it doesn't, so there is no x-intercept. And then it does cross the y-axis. It crosses the y-axis right there, so that would be the point 0, 1. So again, we've got no x-intercept here. This would be the y-intercept. Again, these are x-intercepts right here, y-intercept right here. And I want you to notice something. Notice something about every single one of the x-intercepts. All of the y-coordinates are 0. And notice about the y-intercepts, all of the x-coordinates are 0. Okay? And that might seem a little bit counterintuitive, but it does work that way. So we're going to take a look at the next page, and it says, we have actually seen something like this before, and we've talked about rates before, we've talked about slopes before, and you've probably talked about rate of change in a previous class. Remember, when we're talking about rate, we're talking about the slope. So if somebody says rate of change, we're talking about slope, and that's a really important part of studying graphs and studying functions. So how steep this is and whether it goes up or down from left to right is a really important deal. So we want to write down the slope formula. Hopefully you remember what that is. If we've got 2 points, we would do y2 minus y1 over x2 minus x1. But if we're using function notation, we can actually write it like this. And this is going to look a little bit weird. I'm going to do the bottom part first. I'm going to do x2 minus x1. And remember, these y values are now function values at each one of these corresponding x values. So this is going to be f of x2. And this is going to be f of x1. So remember, x1, y1, those would be paired together. x2, y2, those would be paired together. So x1, f of x1 is paired together. x2, f of x2 is paired together. So what we want to do here is we want to find the rate of change for the functions above from 0 to 1. So from x equals 0 to x equals 1. And to make that a little bit more clear, this is the first x value they gave us, and this is the second x value they gave us. So I'm going to do this one up above here. So this is, I'm going to put an x2 minus, whoops, let me just, I said that and I wanted to write something different. So x2, which is 1, minus x1, which is 0. And then we're going to find the function value here. So this is going to be f of 1 minus f of 0. Notice how those correspond to each other. Now, these are just numbers. I'm just going to leave those like they are, but these are function values. So we want to find f of 1. So we go over to 1, up to right here. So the function value there would be 3. And then we write the minus. Remember, the minus is part of the formula. And then we want to find f of 0. Well, f of 0 is right here, so that would be 3 also. So we get 3 minus 3 is 0, and 1 minus 0 is 1. So the slope, or the average rate of change between 0 and 1 on this one is actually 0. So I'm going to put a box around that, and I want you to think about that for just a second. What does a slope, or what does a rate of 0 look like? Well, a slope of 0 would be perfectly flat. And look, this is perfectly flat from here to here. So from this point to this point, where we found the slope between, it's actually flat. So that worked pretty well. So let's do this next one right here. Again, this one is G, so I'm going to do the same thing again. And actually, I'm going to change colors so we can keep these straight. So this is going to be 1 minus 0. So there's x2 minus x1. And this is, this is going to be, this is a G. So G of 1 minus G of 0. So again, the bottom's pretty easy. It's just 1 minus 0. Now we want to find the function value at 1. So we're going to go over to 1 on the x-axis, up to 1 on the y-axis, or the G of x-axis. So this is 1. And then let's see, G of 0. G of 0. So what is the function value at 0? It is 0. So we get 1 minus 0 is 1 on the top, 1 minus 0 is 1 on the bottom. So that means the slope of this is 1. So the rate of change on this particular function from here to here is 1. And if you stop and think about that, well, that's a line and its slope is 1. You can tell that its slope is 1 because of this kind of stair-step rise run pattern right there. Okay, so we're in good shape on that one. And let's do this last one. We want to find the slope from 0 to 1. So this is going to be, again, x2, 1 minus x1 is 0. And then this is going to be h of 1 minus h of 0. So we're using function values rather than y values, if you want to think of it that way. And again, notice the uniformity here and what's going on here. 1 minus 0, f of 1 minus f of 0. 1 minus 0, g of 1 minus g of 0. 1 minus 0, h of 1 minus h of 0. So the bottom, again, is easy. Now we need to find h of 1. So in other words, what's the function value at x equals 1? So we're going to go over to 1, and we're right here. So it's 2. Okay, minus, again, that's part of the formula, h of 0. When we go to 0 on the x-axis, we have to go right up there. So that would be 1. So this is going to be 2 minus 1. That's a 1. And 1 minus 1, that's a 1, so we end up with a 1 here. Well, notice these two have the exact same rate of change, or the exact same slope. So I'm going to draw a line from here to here so we can kind of tell. And you'll notice that that looks like it is sloped exactly the same as the other one. So we should be in good shape there. I think that looks just fine. Now I'm going to slide down here, and we're going to point out something else. Once we know how to find rates of change, we can actually find something else called the average rate of change. Average rate of change. And the formula is exactly the same as it was before, but instead of finding the slopes for straight lines like we did up here, like this one and this one, we can actually find the slope of a line between 2 points on a curved graph. So instead of being stuck with things that are always just lines like this, the average rate of change allows us to find the slope between 2 points on a curved graph. And if you think about it, we actually did just find an average rate of change in example 3 up above. We found the average rate of change on this exponential curve, and this is curved. I mean, right through here, it kind of looks like it maybe is a little bit straight, but that definitely has a little bit of a curve to it. So finding the average rate of change basically comes down to drawing a line between 2 points on a curve and then finding the slope between them. Remember, if we're finding the average rate would be an average slope, and we can abbreviate that as AROC, so average rate of change. So finding the AROC, the average rate of change, again, we're going to kind of draw a line between 2 points, and then we're going to find the slope between those. So we're going to run into tons of curved graphs, so finding the average rate of change is going to be really useful. So we're going to come down here and we're going to take a look at this, and this is what we want to do on this one. So I need to kind of shrink it down so we can see what's going on here. We want to do exactly the same thing we did up above, but now we're going to be finding the average rate of change from 0 to 2. So it's a little bit bigger than from 0 to 1. We're going a little bit further. So I'm going to come back up here and I'm going to erase that little piece right there. And I'm going to write this down. Again, I'm going to do this one in red. So this is our x1 and this is our x2. So this is going to be, in fact, for this part, I think I'm just going to zoom in on this. Okay. So this is going to be 2 minus 0. And then on the top, we're going to have f of 2 minus f of 0. Again, kind of patterning after what we did right there. And then for this next one, again, it's going to be 2 minus 0. And it's going to be the function value at 2 minus the function value at 0. We'll come back up there and find those in just a second. And then this last one is going to be, this is going to be 2 minus 0 on the bottom. So those are the difference between the x values. And then this is going to be h of 2 minus h of 0. So it's exactly like we did up above, but I want to point something out as we go through and look at this. So I'm going to slide this up here so we can see what's going on there. Okay, so on this one, we want to find the function value at 2. The function value at 2 is right here. So the function value at 2 is 2, minus the function value at 0. Remember, the function value at 0 was 3. So this is a 2 minus a 0 here. So this is a negative 1 on the top and a 2 on the bottom. That right there is the average rate of change. And what I'd like you to notice is this. We found the average rate of change, or the average slope, between these 2 points, 0, 3 and 2, 2. And if we were to draw a line between the two of those, you'll notice that that goes down, which is what we'd expect from a negative slope. It goes down from left to right, but it's not very steep. So negative 1/2 fits that just fine. So now let's take a look at this one. Again, I'll go ahead and put the 2 minus 0 here. We want to find f of 2. Let's go over to 2 and up to 2. Minus f of 0, so that's going to be, again, 0, 0. So this is 2 on the top, 2 on the bottom, so we end up with, and I'm going to, I'll go ahead and fit it in, squeeze it in right there. The slope is 1. Well, that shouldn't be any surprise, because if we went from here to here, it's along the same line, so it's got exactly the same slope. In fact, we could draw the rise and the run on this one. We would rise 2 and run 2, so 2 over 2. We'd end up with that same slope right there, all right? So let's do the last one, and before I actually do the calculations, I'm going to draw the points on here. So this is from x equals 0, so that would be x equals 0 right here, and on the graphic, it's right there, to 2, so that would be way up here, okay? So we're looking for something, and notice that this is kind of interesting. This doesn't even touch the graph. Remember the one we did before? It was kind of right on top of it? This clearly is a straight line between 2 points, and then the exponential function kind of curves around that. So we're going to go ahead and do 2 minus 0 on the bottom, and then we're going to find h of 2, which is 4, minus h of 1, h of 0, so that would be 1. Okay, so this is a 3 on the top, and this is a 2 on the bottom. So that's a slope of 3/2. 1.5. It's steeper than a slope of 1. So there's a slope of 1, there's a slope of 1.5. Okay, so that's how we find an average rate of change, okay? Now, the last thing that we want to look at on this one, and I'm going to go ahead and blow this one up again, we've got a table, and we actually want to connect these dots as smoothly as possible. And we want to say, is this a piecewise function, a linear function, an exponential function, and whether it's increasing, decreasing, or constant, or some combination of those. So let's go ahead and graph these points right here. This ought to be pretty quick. So we go negative 4 and 3, so that would be right there. Negative 2 and 2, so right there. 0 and 1, right there. So it looks like it's pretty straight there. And then 1 and comma 0.5, so 1 and 0.5. Yeah, that looks pretty straight there. And then 4, negative 1, so it'd look like this. So if we connect those, because it does say connect them with a nice smooth graph if we can. So we're going to make that nice smooth graph right there. We'll assume that it continues. So this is going to be linear, definitely linear because it makes a line. Remember, the root word of that is line. So we've stated that, and we want to state whether it's increasing or decreasing. This is definitely decreasing because as we go from left to right, it's going down. So we start up here, and as we go from left to right, then it's going to go down. Okay, let's look at this one. We've got negative 2, 4. So negative 2, 4. So the x is negative 2. The function value is 4. The x is negative 1. The function value is 2. The x is 0. The function value is 1. And then 1, 1/2, same thing as we had before. And you can tell that might have looked a little bit like a line right here, but now you can really tell it's starting to curve. And then 4, 0.25. So if x is 4, then the function value is 0.25. So it's maybe about right there. So if we were to connect those, it would look something like this. And it takes a little bit of practice to draw these pretty well. Again, we'll assume that it goes like that. So this is going to be, well, that's, gosh, if it's got that curve to it and it's kind of coming out here and flattening off, that is going to be exponential. That's going to be an exponential curve. And this, again, is decreasing. It's decreasing because it goes down from left to right. All right, last thing here, and this is really important. Okay, these are the types of functions that we're going to study just this year. We're talking about piecewise, linear, and exponential. There are tons of different functions that you're going to learn about, lots of shapes and sizes and weird stuff going on and things like that. So here's our goal. Our goal is to become familiar with the vocabulary and the fundamental features of functions so that we can identify them in this class and we can use those ideas in future classes. All right, go ahead and do the self-assessment and good luck on the assignment.